Okay, thank you very much. Can you all hear me? Okay, thanks. Today I'm going to talk about code-based cryptography, which is the type of post-quantum crypto systems based on coding theory. We'll see later what this means exactly. So this is today's outline. I think in the first half of today's talks, I will talk about coding theory. Well, of course, not everything, because the time is limited, and a bit about what code-based cryptography is doing. And I'll also go through the main attacks against code-based cryptography, and also some other minor attacks. In the second half of my talks, I'll talk about classic McLeese, which is a submission to the NIST PQC standardization process. And also I'll talk about some other types of code-based crypto systems that was also involved in this NIST PQC standardization process. What I'm not going to talk about is, well, signature schemes. Well, people have been trying to use code-based crypto to build signature schemes, but for me, this is not a very important topic. Personally, I would say I'm satisfied with using just hash-based signatures. So yeah, so this is not going to be today's topic. Yeah, 2 years ago, I also gave a talk about code-based crypto, and at that moment, I was too greedy. So eventually, I used up all the time. So today, I didn't really prepare so many slides. Anyways, let's see how it works. Okay. So first of all, I would like to say a little bit about the basic mathematical background I think we need to have. Of course, many of you should already know this, but just in case you don't really know, let me try to recall what finite fields are. So a finite field is a finite set with two binary operations. Well, there are some other properties these two binary operations need to satisfy, but well, let me just omit it. There are going to be two elements, 0 and 1, in the finite field. 0 is the additive identity. So this means that, well, for whatever alpha in this field, you can add it with 0, and then you will get the original element. For whatever alpha in the field, you can also multiply with 1, and then you will get alpha. And you also have an additive inverse. So for each element, you can you can find an additive inverse minus alpha, so that when you do alpha plus minus alpha, it becomes 0. For each non-zero element, you can find a multiplicative inverse, such that if you do alpha times alpha inverse, then you get 1. Okay. So this might sound a bit abstract. So if you need a concrete construction, here is how you can do it. So basically, every finite field is going to have the number of number of elements in the finite field is always going to be p to the k for some prime p. And in the case when we have k equals to 1, then the structure of it is the same as ZP. Well, ZP is basically, we can imagine that you're doing integer multiplications and integer additions, but when you try to compute the result, you do modulo p in the end. And when k is greater than 1, the structure is, well, equal to this fp of x over f of x, where f is an irreducible polynomial over fp. So what this means is that you try to do computation in this ring P of X. So this is just the polynomial ring where the coefficients are from Fp. And then when you do additions and multiplication, you always do modulo F in the end. So I think this is not really hard to understand. Maybe the notation is a bit scary, but it's really easy concept. And in this talk, we'll mainly talk about characteristic 2 fields. These are the fields where P is equal to 2. And of course, F2 is one case. And one important property is that for any element in a characteristic 2 field, you have alpha plus alpha equal to 0. In other words, you can consider that there's no minus. Well, minus is the same as plus because, well, if you want to find the additive inverse, then it's just the element itself. So in some sense, you can consider minus as just equal to plus. Okay. So now we can start to talk about what coding theory and error correction is about. So I think the motivation of doing coding theory was that people want to transmit a message through a noisy channel. By noisy, I mean the channel is not totally reliable. When you transmit the message, some bits of the message can be flipped, like 1 becomes 0 and 0 becomes 1. So if you just don't do anything, then, well, receiver can receive a noisy message, and, well, probably for him, he wouldn't know what the original message is. So coding theorists, well, started to think about how to deal with this. So the method they came up with was like, okay, we try to encode our message into a coword. Well, coword is a vector in a larger space. And this larger space is a specific set of vectors. That's the code we're talking about. So you try to somehow encode your original message into one of the vectors in this larger set. And then you still you send this coword through the channel. And then, of course, some bits are flipped. Well, there might be some bits are flipped. But even if this happens, as long as there are not so many errors, the receiver can recover the original coword by using an decoding algorithm, or we might call it a decoder. And then from the coword to message, it's usually a very trivial process. So yeah. So yeah, I should say that, okay, by encoding, usually people talk about this process of converting M to C. And by decoding, usually people are talking about converting C plus E to C. They are usually not talking about C to N because, well, this is really trivial concept. Okay, so here in this page, yeah, we see many things, but many things are still not quite well defined. For example, what do I mean by not so many errors? Well, we will see how these are properly defined later. Okay, in this talk, I'll talk about well, linear code. I'll consider just linear codes. There are other types of codes, but for me, for the purpose of talking about code-based crypto, it's not so important. So I'll just talk about linear codes. And linear codes, a linear code is just length n. Well, a linear code C of length n and dimension k is just a k-dimensional subspace of this fq to the n. Well, fq to the n is just the vector space over fq, and where every vector is of length n. Okay, so if you have learned linear algebra, this should be quite easy to understand. So since a code is just a linear subspace, you can of course represent it as the row space of a matrix, or I should say K times N matrix, G. Yeah, and then, yeah, of course, by definition, this row space consists of the result of multiplying all kinds of length K vectors by G. And of course, you can also represent the code as the kernel space of parity check matrix, H. And then H is going to have dimension n minus K times N. Okay. Yeah, as I write here, I'll often omit the transpose sign in later slides. And some more terms. So if you have a vector, or whatever vector it is, it doesn't have to be a coword. So if you multiply a parity check matrix by a vector, then this becomes a syndrome of the vector with respect to this parity check matrix. And if you consider the row space of the parity check matrix H, then we call this set the dual code of the original code C, and we will denote it as C perp. Okay, here's a very trivial example. So you can consider the following code over G of 2, and it's of length 7 and of dimension 4. So you see this generator matrix has well, dimension 4 times 7. And you can, of course, very easily create the corresponding parity check matrix using linear algebra. And then, of course, whatever vector that you use to multiply with G, then this will become the coword. This is very trivial. And of course, for whatever coword you created, when you multiply by H on the left, then it becomes 0. Here we can see that actually G has the identity matrix on the left. And if you have this kind of form, you can easily create the corresponding parity check matrix by transposing the non-identity part. Okay. Okay, now we can talk a little bit about like what I mean by not so many errors. Okay. So first of all, we need to know what's called Hamming weight. So Hamming weight is just Hamming weight for whatever vector is just the number of non-zero coordinates in that vector. For example, here we have a 1, 0, 0, 1, 1. Then well, the number of non-zero coordinates is 3. So the Hamming weight is 3. And you can also consider Hamming distance of 2 vectors. Yeah, in this case, you're considering the number of different coordinates in these 2 vectors. For example, we have 1, 1, 0, 1, 1, and 1, 0, 1, 1, 1. So the second and the third coordinates are different. So well, the Hamming distance is going to be 2. And here's the most important term in this slide. So the minimum distance of the linear code is, well, I think you can probably guess by seeing the name. This actually means the smallest Hamming distance between any 2 cowords in this code. And equivalently, because well, the difference of any 2 cowords is going to be, well, also coword because we are working on linear codes. So you can consider that minimum distance is also just the smallest Hamming weight of a non-zero cowords. in this code. Okay. Yeah, please try to remember the concept of minimum distance. We'll get back to it later. Okay, now I would like to talk about what I mean by decoding. Yeah, there are two types of general decoding problem that we usually talk about. So in this, the first one is regular decoding. In this case, we're given a generator matrix G and a vector X as inputs, and then we want to find the minimum weight E, or equivalently C, such that X is equal to C plus E. Okay. And the second form of general decoding problem is that, so we're given a parity check matrix H and some vector S, and we want to find the minimum weight E such that S is equal to H times E. Okay, so the two problems are actually equivalent in the sense that you can easily reduce one to each other. So, for example, if you start with a regular decoding instance, here is you're given X, then, well, you can multiply it by any parity check matrix H, and then this will become, well, Hx equal to Hc plus He, and then it's because Hc is just 0, so you get He. And then you can solve it using a syndrome decoder. If you start with He, then you can use linear algebra to easily compute some x, some vector x, such that Hx is equal to He. And then this x is going to be the sum of some coword plus the E you want to find. Okay, so in this sense, the two problems are equivalent. And sometimes people talk about some other variants, like having different constraints on E, like weight being smaller or equal to T, or weight equal to T. But anyways, I don't want to talk about the slight difference of these variants. In this talk, you just need to consider these problems as well-studied, computationally hard problems in code-based crypto, as long as G and H are random. Okay. Okay. Now we can talk about like why we are interested in minimum distance. Why it's important for codes. The reason why we like to find minimum distance is that we want to know how many errors we can correct using this code. Okay, so okay, basically, if you consider any vector x which is equal to C plus E with the Hamming weight of E being smaller than d over 2. Well, here d is the minimum distance. Then this vector x can be uniquely decodable to C. This means that you can find a unique coword such that it's the closest one to this vector x. Okay, I think it's already very clear by seeing this picture that this will happen. But you can consider the opposite case, like, for example, if you have t equal to d over 2, then you will see that, okay, this vector x will lie in the middle of two cowords. And you don't, in this case, you don't really know which one. You cannot say, okay, this one's the closest, this one's the closest, because there are two solutions for this. Okay. And well, if you like, you can also try to turn this in an equivalent way. So you can say that the code can always correct t errors as long as b is greater than or equal to 2t plus 1. And you can also say that, okay, the code can correct d minus 1 over 2. You take 4, so many errors. And finally, I should note that well, having t smaller than d over 2 doesn't really mean that there's an efficient algorithm for decoding t error. This just means that if you, for example, if you try to exhaustively search through the whole code, try to search for every vector in the code, and then you should be able to find the unique closest code words. It doesn't mean that you have a very efficient algorithm to do this. Yeah. Okay. Now we can take a look at another example. So here we're talking about Hamming codes. So you can see that I have a parity check matrix, which is actually the same as my previous example. So it's a parity check matrix for a length 7, dimension 4 code. And you can notice that the columns are just binary expansions of 1 to 7. Okay. And now, if I ask you, like, what's the minimum distance of this code, then yeah, maybe you can start to think about how can we really find this minimum distance. So yeah, you can start to think about, okay, what's the definition of minimum distance? Well, it's the minimum Hamming weight of any code word in the code. Okay, and you also know that if you have a code word and you multiply with h on the left, and then you will get 0. Okay, so this means that actually you can consider, like, if the minimum distance is 1, this should mean, like, if you pick one column from this parity check matrix H, then it should be possible that this vector is 0, because, well, this is going to be the product of H and E. Okay, and then you can consider, okay, 1. Okay, there's no 0 vector, 0 column in this parity check matrix, so certainly minimum distance is now 1. And then you consider 2. Okay, apparently if you pick any 2 columns in this parity check matrix, then they are going to be different. Okay, so you cannot have like a weight 2 code word that, well, when multiplied by h becomes 0. Okay, and how about 3? Well, for 3, certainly you can see many possibilities. So we can certainly pick 3 columns from this parity check matrix so that they sum up to 0. Okay, so yeah, the minimum distance is, well, actually 3. And then you think about my previous slide, okay, in this case, how many errors can we correct? Okay, then, okay, you might think about, like, okay, we need to be t, the value t need to be smaller than d over 2, and d over 2 is like 1.5. So at most, you should be able to correct just 1 error. Okay. Yeah, and here we can also present a very trivial decoding algorithm. Well, in this case, the decoding algorithm is very trivial, but often if you have some more complex construction for the code, then decoding algorithms are also more complex. But in this case, it's very trivial. So if you have a received word R, which is C plus some weight 1 error vector E, and then you can just multiply this R by your parity check matrix to get a corresponding syndrome S. And then this syndrome is going to be equal to HC plus HE, which is just HE. And then because the error vector is just weight 1 vector, so this will help you to find this syndrome will indicate like which column is a 1 corresponding to the error position. Yeah, I should say this is really a very, very trivial example. If you take a look at the some textbook of coding theory, then you will see much, much more complex codes. But okay, today I decided not to talk about very difficult things. So yeah, you just need to know, okay, we can actually correct some errors, and yeah, we can have efficient decoding algorithms. Okay. Now I can start to talk about code-based crypto, what code-based crypto is actually about. So everything about code-based crypto was started from this MacLeese crypto system. And this system was presented in 1978. So you can see that it's a system that has a very, very long history. Yeah, it's already more than 40 years now. And in this crypto system, the secret key is going to consist of a generator matrix G, and also a random permutation matrix P, and a random non-singular matrix S. And the last piece of the secret key is going to be some kind of information that you need to decode C. Here I should probably say a bit more about like how this secret key is defined. So if you look at some other references of the MacLeese crypto system, then okay, sometimes they would say, okay, it's just GPS, or they would say the last item is just some efficient decoding algorithm for C. But for me, this is a bit confusing, because when you talk about decoding algorithm, I think often you're talking about how to decode a class of codes. But for decoding some specific code, then you still need some specific information for that code. Okay, so this is why I add this fourth item here. And I should also mention that in many cases, you can actually combine the first item with the fourth item. In many cases, with a special generator matrix or a special parity check matrix of the code, then you can already do efficient decoding. This is a very common case. Yeah. Okay. And then the public key is going to be this G hat, which is the product of SGP. So the reason why we're doing this is that we want to scramble this generator matrix G so that other people cannot find the secret structure of it. And as I mentioned, in many cases, if you use a special G, then often this already implies that you can decode the code C very efficiently. So of course, this kind of structure should be hidden. Yeah. Okay. And yeah, you can consider the public key size. Well, it's the size of the parity check matrix, so it's k times n field elements. Okay, and later on I'll show that the main idea in this system is that we try to make G hat a random matrix, and then we use it to create an instance for regular decoding. And what we hope is that, because we hope that G hat looks sufficiently random so that the best an attacker can do is to solve the general decoding problem. Of course, the attacker can still try to find the structure inside this G hat, but well, this is what we hope to happen. Yeah. Okay. And yeah, as I mentioned, when you do encryption, you're creating an instance for regular decoding. So you have a message that you want to encrypt. This is a length k vector n. And then you will artificially generate a uniform random error vector e, which is of weight t. And then you just compute y equal to n g hat plus e. This is going to be your ciphertext for the message. So this y is going to be transmitted to the receiver. So you have y being public and you have g hat being public. So yeah, this is just the same as the setting of regular decoding. And for decryption, the one who receives this ciphertext y, he can multiply y by p inverse, and then you will get n g hat p inverse plus e p inverse. If you think about this, this is actually the vector ns times the generator matrix G plus an error vector EP inverse. Well, here EP inverse is just something that has the same weight as the original error vector E. So yeah, you can consider this as an instance for decoding. And yeah, so because of this, you can use some decoding algorithm to find this vector ns from nsg plus ep inverse. And then from ns, it would be very easy to compute the vector m. Okay, here's another very famous code-based crypto system. This is the Niederreiter crypto system. So as you can see, everything in Niederreiter crypto system is very similar to McLeese. It's just that we start with a parity check matrix H for the codes. And then we also have this random permutation matrix P and random non-singular matrix S. And of course, we need some kind of information for decoding C. Okay, these are going to be your secret key. And then, as in the McLeese crypto system, we try to scramble this parity check matrix in a way that we create the public key H hat by multiplying S, H, and P. And then, you can also consider what's the public key size in this case. Well, in this case, because we are using parity check matrix, so the dimension is going to be n minus k times k field elements. Okay, so the main idea behind this, behind Niederreiter, is just very similar to McLeese. You want to create a random-looking instance for the syndrome decoding problem. Okay, so as you might have expected, when we do encryption, well, actually we're considering weight t error vectors as our message, and then after you encode your message into this error vector, and then you can just multiply the error vector by your public key H hat to get the ciphertext S. Okay, so now you have H hat being public and S being public. So, well, this is the same setting as in the syndrome decoding problem. And then you can also use your secret key to decode. So the process is like when you receive the syndrome S, you multiply it by S inverse on the left. And then, yeah, you can see that this is going to be S inverse times H hat E. And then you expand H hat into X S H P, and then you can see that this S inverse and S cancel out. And then eventually we have H times PE. Now PE is, again, a weight T error vector. So, well, this you can use your syndrome decoder to find PE. And then when you find PE, it will be trivial to find E also. Okay. And we often say that Niederreiter is a variant of Michaelis. And, well, this is not just because they look very similar. There's actually some theoretical foundation for this. You can actually prove that in the setting of what we call one-way CPA, OW CPA setting, breaking Niederreiter is just the same as breaking Michaelis. Okay. Okay, now we can talk about some more practical issue like how to reduce the key size. So a very standard way to reduce the key size is just to use the systematic form of the parity check matrix or the generator matrix. What I mean by systematic form is that, for example, if you have the identity matrix of dimension k times k on the left in the generator matrix, then we call that this is a generator matrix in systematic form. And, yeah, similarly, if you have an identity matrix in the parity check matrix, then, well, we can also say that this is a parity check matrix in systematic form. It doesn't really matter where the identity matrix is. It's just that we need it to be somewhere in the public key. Okay, and then because you know that there's going to be a identity matrix on the left or on the right, yeah. So for that part, you no longer need to store the entries because you already know what the entries are. So what you need to store is just the entries of this matrix Q. Okay, so, yeah, this is going to save you some size. Yeah, we can take a look at this table. So, so for both Michaelis and Niederreiter, if you just use systematic form for the generation matrix or the parity check matrix, then you can reduce the key size to k times n minus k. And by the way, using Niederreiter has an additional advantage, which is that the ciphertext size is going to be slightly smaller. So because we're using syndrome as the ciphertext, so, yeah, it's going to be of size n minus k compared to size n ciphertext in Michaelis. Okay, so I think what you should notice that this actually doesn't happen for all the secret keys in Michaelis or Niederreiter crypto system. Yeah. It's very likely that you have, for example, you generate a secret key, and then you try to generate the corresponding public key, and then you realize that this public key cannot be reduced to systematic form. Now, this is a very trivial fact if you know something about linear algebra. So yeah, the bad thing about using this is that we might need to generate secret key a few times until we find a corresponding public key, which can actually be reduced to systematic form. And for very small q, for example, when q is equal to 2, then this number is going to be something like 3.4 or 3.5. Yeah. And this can increase your key generation time. So if you don't really know how this number is calculated or how it can be calculated, then I actually have an exercise for today's talks. And yeah, you can think about how to like really write down a formula that tells you what this number is. Okay. Okay, now we can take a look at like a more commonly used code. I think Hamming weight is usually just what people use in textbooks, but in reality, people usually use some more complicated code. And here is an example. So binary Gopa code is actually what Maclise proposed together with the framework, the Maclise framework. So he actually says that you should use this framework together with this specific code, binary Gopa code. Yeah, he didn't say that okay, you can use any code. Yeah, I think the reason should be quite clear because as you can imagine, if you use some bad code, then it might not be secure. Yeah, so you need to choose. Well, by your best knowledge, what's a good code? What kind of code? When you use it in Maclise or NeedWriter, it can result in a secure crypto system. And for some reason, Maclise, even though it was just more than 40 years old, more than 40 years ago, he still managed to pick the right option. Because binary Gopa code is still not broken today. Okay, so now I can talk about the definition. So if you want to create a binary Gopa code, you first have to consider some field size q, which is 2 to the n, and then you will create a list alpha 1 to alpha n of n distinct elements in the field. Okay, because they are distinct, so you can see that well, this number n is going to be smaller or equal to 2 to the n. And we will call this list the support of this code. And then you will have a polynomial, a degree t polynomial g, which is over fq. And the constraint on this polynomial is that so g of any alpha I shouldn't be 0. So any alpha I shouldn't be a root of this polynomial. Okay, and we will call this polynomial g the Gopa polynomial. And then with these two elements, the support and the Gopa polynomial, you can create a binary Gopa code, which we usually denote as gamma LG. And the definition is like what I wrote here. So you consider all the lengths n vectors over G of 2. And then some of them are going to be your cowords. And the constraint is that, so C1 over x minus alpha 1 plus C2 over x to the alpha 2 and so on. This is going to be 0 modulo your Gopa polynomial. Okay, if the length n vector satisfied this constraint, then we said, okay, this vector is going to be one of our cowords. Okay. Now, for some of you, maybe the notation here are not so, maybe you are not so familiar with the notations here. So I should say that, okay, here I use, well, 1 over x minus some alpha I. Well, this actually means the multiplicative inverse of x minus alpha I when you modulo g of x. This means that it's actually a polynomial that when you multiply with x minus alpha I, it becomes 1 when you modulo g of x. Okay. Okay, and then if you really understand this definition, you should be able to convince yourself that, okay, this set C, it is actually a linear code over GF2. Okay, so please be careful. Although we have the field GF to the n, GFQ, but actually this code is going to be just over GF2. Okay. Okay, so now I can talk about some properties of this gamma LG, where degree of G is T. I'm not going to talk about proofs because I tried to do this 2 years ago and realized that, okay, it took too much time. So if you really want to find proofs of these properties, then yeah, please take a look at some commonly used textbook for coding theory, and you should be able to find proper proofs. Okay, so the first property is that the dimension of the code is going to be at least n minus mt. And yeah, for the parameters that we usually use in code-based crypto, usually equality will just hold. Yeah, but just in case, you shouldn't exclude the possibility that k is greater than n minus nt. Well, this is actually something that should be very, very easy to prove. So I think you should try to do this by yourself. The second property is that the minimum distance is going to be at least t plus 1. The third property is that actually gamma LG is going to be the same as gamma L G squared when G is square free. Here I should explain what square free means. This actually means that you cannot find a non-trivial factor of G. Let's say this factor is called alpha, such that alpha squared is also a factor of G. Okay. And now this you might feel that, okay, you don't really know why we need to know this, but if you combine the second property with the third one, then you can actually conclude that the minimum distance should be at least 2t plus 1. Okay. And now you see that suddenly the minimum distance increased from at least t plus 1 to at least 2t plus 1. So we should be able to decode more errors, of course. So now we are able to correct t errors, where t is the degree of our Goldbach polynomial G. Okay. And MacLeese actually suggested to use irreducible G's. So he didn't say that, okay, you can just use any square-free G's. He said, okay, you should just use irreducible G's. And yeah, so you can imagine, well, for irreducible polynomials, the only factor, non-trivial factor you can find is just itself. So of course, being irreducible implies being square-free. Okay, and finally, there exist efficient T-error decoding algorithms when G is square-free. And yeah, unfortunately, I don't have time to present it, but you can, if you want to search online, you can try to search for these keywords like Patterson algorithm and the Berken-Massey algorithms. These are pretty famous algorithms in coding theory. Okay. Yeah, I think I already finished the very first item. So is there some questions so far? Okay, I don't see any, so let's continue. Okay, now I would like to continue with the main attacks against Macley's crypto system and Niederreiter crypto system. And these algorithms are what we call ISD algorithms, information set decoding algorithms. Okay, and yeah, here for today's code, consider things in the Niederreiter setting. So we have some parity check matrix H, and we have some syndrome S, and then our job is to find a weight T, a vector E, such that S is equal to HE. I think it's very easy to see that if you can solve this, then you can break Niederreiter. Okay, but of course you can also take the view of generating matrix, and then you can have ISD algorithms working against the Macley's crypto system. Okay, so first of all, I would like to talk about the general structure of ISD algorithms. So ISD algorithms are, for any of them, it's going to be iterative. So it consists of a sequence of iterations. Now you can consider that these iterations are all independent. And then in each iteration, at the beginning of each iteration, you always do the same thing. So what you do is that you're going to permute the columns of the parity check matrix by multiplying it by a permutation matrix. And then you're going to multiply HP by some non-singular matrix S, such that the result H prime is going to have systematic form. Okay, and you should notice that we also need to multiply the corresponding syndrome by this matrix S. Okay. Yeah, of course you might encounter the case that HP cannot be reduced to systematic form. And then, one simple solution is that you just skip this iteration and then start with a new iteration. But of course, there are some other better solutions, but I'm not going to talk about that. Okay, and at this moment, you have, some H prime and S prime. And then, actually, this is like a twisted instance for the original syndrome decoding problem. Okay, so now you can try to solve the syndrome decoding problem with input H prime and S prime, and then you should be able to find some error vector E prime. And then, by the last item here, you can actually see that this error vector E prime can be converted to a solution for the original problem S equal to HE. Okay. This is not so hard to see. Yeah. So yeah, I think I should emphasize that actually the main idea is to permute the columns. This is a very important thing in ISD algorithms. Okay. So now we can take a look at a very old ISD algorithm, which is the branch algorithm. In this algorithm, actually we will have we try to, in each iteration we try to guessing that the form of the error vector corresponding to this iteration is going to be like what I show in this picture. So it's going to have 0 ones in the first k entries, and then in the last n minus k entries, it's going to have t ones. Of course, you can see that this happens with a very low probability, right? So if you consider that you're just doing random permutation of columns in each iteration, okay, at some moment you will encounter this case, but well, this happens with a very low probability. But anyways, this is how the algorithm works. So in each iteration, we try to compute this column permuted parity check matrix H prime. And then in order to see whether such a solution exists, we check if the corresponding syndrome S prime has weight equal to t. If we have a weight t syndrome S prime, and then I think it's very easy to imagine that, okay, we can put this S prime as the last n minus k entries of our error vector, and then we find a solution for the problem of finding E prime for S prime equal to H prime times E. Okay. As I mentioned, this algorithm is very old and it's not very efficient. The success probability for one iteration is extremely low. You can actually try to compute the exact probability. And because of this, Libricel tried to improve the algorithm a little bit. So he said, okay, in order to increase the success probability, we will consider that in the first k entries of the error vector, we will have p errors instead of just 0 errors. And you should be able to imagine that this will largely increase the success probability of each iteration. Okay. And what we have to do in each iteration is that we will enumerate through all the sums of p columns of t. And then for each sum in this set, let's call this sum V. For each sum here, we will try to check if the weight of V plus S prime is going to be T minus P. If this happens, then this means that, okay, by how you created the vector V, you know that which entries in the first k entries are ones, And then with the vector v plus s prime, you can find a solution for the last n minus k entries. Okay, so this is how it works. So the concept is to increase the success probability for each iteration. And then we have a slightly more complicated variant, Leon. So I think the main concept, main idea in Leon is that so Leon want to make use of early aborts. So the concept is like you don't really do the check for all the rows of the instance. You first try to find solutions for the first row block. And then only if you find solution for that problem, you continue to check if your solution fits the second row block also. Okay, I think this is the main idea in Leon. And in Leon, we'll consider an error distribution like having P, 0 and T minus P in the K, L, and N minus K minus L entries. Okay. So as I mentioned, you want to do an early abort. So first of all, you just do something that's essentially the same as in what's that called? Sorry, LibreCal. In the LibreCal, so you just try to enumerate all the sums of P columns in this matrix T1, and then you check if any of them is equal to S1 prime. Okay, if this happens, you already find a solution for the first row block. And then once you have such solution, you check the second row block by checking whether the corresponding sum of columns of this matrix T2, that's called this sum V2. And then you check whether V2 plus S2 prime has weight T minus P. If you have weight T minus P, then okay, you also find the part of this T minus P, the part for the last N minus K minus L entries. Okay. And then we have the Stern algorithm, which is an important improvement over Leon. So Stern basically want to, in Stern, you try to make use of a collision search to accelerate the algorithm. Okay, so the concept is that, so now you consider that you have P errors in the first K over 2 entries, P errors in the K over 2 entries. Okay, and then as before, you try to enumerate through, you try to generate all the sums of P columns of this matrix T11, or the sums of P columns of T12. And then you try to do a collision search between these two lists. I should be more careful. So you try to do collision search between the first list and the second list, where every element is added by S1 prime. Okay, and then you try to do collision search between these two lists. For example, by using a hash table. Or there are also other ways, like, okay, you try to sort for example, the first list, and then for the second list, every element of the second list, you try to do a binary search to find a collision between these two lists. Okay, and as before, if you find a solution, if you find a collision, then this is going to tell you a solution for the first roadblock, and then you can try to check for the second roadblock. Okay. Okay, and there are also some more recent attacks. So the first one is this MNT attack. Yeah, so as you can see, this is a bit fancier than the previous algorithms. So in MNT, the distribution of the ones in the error vector is going to be like in this square, this rectangle. So it's going to be have 2p errors, and then t minus 4p errors. And this 2p errors actually comes from some p errors plus p errors. Okay, and also this 2p errors comes from some p errors plus p errors. Okay. So in MNT, I think the main idea is that they want to make use of multiple level collision searches. So in Stern, it's like just one level collision search. You only need to do collision search once in each iteration. But here we have to do a 2-level or even 3-level collision search. And another important concept is that in MT we try to make use of multiple representations. We want to create multiple representations for one solution. Okay. So by looking at this picture, you should be able to imagine what this means. So even if you have a solution like having 2p errors here, 2p errors here, you might have many different ways of picking the first p errors and then picking the second p errors. So this is why we have multiple representations in MNT. Okay, and then we can see how the multiple collision search works. So again, we try to compute the sums of p columns for this submatrix. We try to compute the sums of p columns for this matrix. And the corresponding lists are going to be called L1 and L2. Okay, and then you first try to find a solution for this part. And for this part, what you do is that, okay, you try to find collision between vectors in L1 and vectors in L2 plus some delta, where delta can be some random vector that you pick. Okay, so this is one collision search. And then you also do something similar for this part. Okay, so now it's everything is similar except that the second list consists of the sums of p columns plus S1 prime plus delta. The reason why we are doing this is, I think it's quite obvious, because we want to find V11, V12, V11 plus V12 plus V11 prime plus V12 prime equals to S1 prime. Okay. So okay, for this one we have one collision search. For this one we have one collision search. And then once we find solution for V11, V12, V11 prime, V12 prime, then we can continue with the second row block. In this case, we will still have the first list and the second list, and then we will do another collision search to try to find the solution for the second row block. Okay, so things are getting more complicated because now you can see that we need to do like three times collision search. Okay. And the most recent one is this BJM attack. I think it's this algorithm is very, very similar to MMT algorithm. Yeah, so the main concept is just that, okay, for the base list, it's going to have, they are going to have like P plus epsilon errors. And then when you try to add this part to this part, you allow this part of alpha errors to cancel out. Okay, and somehow magically this brings some advantage in terms of complexity. I think, well, if you don't really understand this, I think it's very normal because things are getting very, very non-trivial in this case. Okay, and here's a summary of the ISD algorithms I presented. So, okay, maybe you can try to recall what I said before. So for prompt, it's like 0 errors and T errors. For Libricode, it's P and T minus P. For Leon, because we want to make use of early aborts, so there are going to be L entries which are not in error. Yeah, and then for the rest of the entries, Leon considers that they have P errors and T minus P errors. And for Stern, Stern tried to divide this the errors in the first K entries into 2 parts. So this is why we have P, P, and then finally T minus 2P. And then we have the fancier algorithms MMT and BJN. Yeah. Okay. And actually, some people have already tried to use these ISD algorithms to attack real systems, real MAC-list crypto systems that people proposed. So, for example, the original parameters proposed by MAC-list himself is like, okay, you have M, N, K, T equals to 10 and 10, 12, 524 and 50. Well, this is not a very not large enough, but somehow maybe because at the time MAC-list proposed the system, it was still early years of the development of public key cryptography. So at that moment, people don't really know how to set up, how to consider the capability of computers, for example. And that's very crucial for setting parameters. Okay, so, okay, it turns out that MAC-list designed a relatively small system that can actually be broken by ISD algorithms. So Bernstein, Langer, and Peters actually tried to use their software for Stern to break the system. But it involved like 200 computers and about 300 cores. But this is actually a 2008 attack, so at that moment the computers are also weaker. Yeah. And there are lots of optimizations you can do in practice. So what I just described is just some very basic version of the algorithms. So for example, you can when you do the column permutations in each iteration, you can actually do a bit better. You don't have to do a full permutation for all the columns. You can just swap like X columns in the n-k columns, and then you swap this columns with X columns you pick for the remaining k columns. And then this x can be very small, like well, smaller than 10 or something. And then it will still give you a very good permutation. So this already saved quite some operations. And there are also some efficient way to generate the base list. So by base list, I mean like, well, for example, you in the algorithms I showed, you often need to compute the sum of p columns of some matrix. And there are much better ways to compute this list. Yeah, you can save quite some operations by doing something clever. Maybe you can think about it. And finally, yeah, in Stern or Leon, they have like L entries being error-free. And one optimizations used by Bernstein et al. Is that, okay, we can have several candidates for this set of L columns. Okay, and okay, this means that, well, MacLeod's crypto system is broken. I think it's unfair to say this. Often people, the failure of people is that so they often don't really know how to design the parameters. For example, MacLeod's the 40 years old, it was really too early for public key cryptography. So I think it's not really his fault for designing a crypto system like this. But today, we know much better about how to like evaluate the capability of computers and so on. So yeah, we know how to design proper parameters for MacLeod's and Niederreiter crypto system. So solution is just, well, try to use larger parameters, try to use what people design today. Okay, yeah, I think I'll end here, and I'm glad to take some questions if you have any.
那个有任何问题吗？这个要问用中文也是可以了。Any questions？
喂，您好，我想请问前面投影片问到那个 Peterson 演算法和 Berkeley 跟 Marseille， 他们两个在做 decoding 的时候，哪一个比较好，或是说比较适合那个密码用途？谢谢。
这是个有趣的问题，就是 Okay, I should speak in English. So this is an interesting question, I would say. So yeah, I think currently the state of the art implementation, which is written by myself, is using Berkeley-Marseille algorithm. Yeah. I think one reason for using Berkeley-Marseille for the current implementations is that I think it's quite efficient for doing constant time implementations. Yeah. So, of course, if you really want to understand this, then you have to look at my papers and see how everything works. But well, it turns out that everything fits very well with constant time implementations. And yeah, for Peterson, well, I should say I have never really tried, but well, I actually have some discussions with Ruben also about whether Peterson can beat Berkeley-Marseille or not. And yeah, I would say probably a very highly optimized version of Peterson would be slightly slower than Berkeley-Marseille, I would say. But this is something that people should really try to study and try to see how it works. Yeah. So I would say this is something that hasn't been really studied very well. But my guess is that Patterson will not be able to beat Perkin and C. But I guess the difference won't be very big also. Yeah. If you want, this can be a small research topic also. Yeah. So, is there some other questions?